Good afternoon. As Alan just said, we have a unique technology that we're developing for clean power and green hydrogen. And I'll take you a little bit through our journey and what we're doing, and also how this fantastic technology that we have that was spun off from Imperial College and now has been matured and has applications all around the world, really. I think that the simple concept that I'm going to talk about is that uh, we have a metal supported solid oxide technology. So we are considered the leading technology in the world for this. And what started off as a simple idea at Imperial College, where could we make a solid oxide on a metal support, has now transformed into obviously lots of different patent families and technology that has matured. So we have a very unique technology whereby we operate our solid oxide at a low temperature between 500 and 600 degrees C, and I'll show you in a bit. And the other innovation of our technology is that we have a Syria-based electrolyte. So most solid oxides have yttrium stabilized zirconia as the electrolyte. And our innovation is that we were able to use Syria as an electrolyte. So we're metal supported, and we have a new electrolyte that allows the temperature to be lower than other solid oxide fuel cells or solid oxide electrolyzer. These two innovations really allows for this technology to make products which are very, very cost effective and robust. And that's the attractiveness for our customers to adopt this technology. And the other unique thing about our company is that we obviously started off with thinking we'll make products, but we actually license our technology to world-class companies all around the world. And they take our recipes for the materials, but also our manufacturing expertise, and and we work with them so that they can take these technology to products at scale and at pace. And our headquarters is in Horsham, West Sussex, where we have about 500, let's say, engineers and scientists. But we also have a manufacturing facility in Redhill, close to London, where we can make up to 2 megawatts of this. So that allows our customers, and they come from all over the place, Japan, Asia, Europe, America, and they come and actually they're able to see in a manufacturing environment how this technology is translated into actually a manufacturing floor and how we make our fuel cells and electrolyzers products. And then they license it to take it to wherever they want to make factories all around the world. So solid oxide is a fully reversible technology. So as we said, you can take fuel in and with a solid membrane with air on the other side, you can basically produce electrons. So it can work with hydrogen very well, but it can also work with other fuels like natural gas. And I'll show you some of the other fuels. It is fuel flexible. But the other thing is you can run it in reverse, and you can take the same set of materials and you can run it in reverse, and you can put steam in, and you can basically make hydrogen out. And if you could think about it, if you can use renewables in, then you make green hydrogen. So that is also something that's of huge interest, and we are using our technology to do both. So as I said, we were spun off from Imperial College slightly over 20 years back. And our founders are here. I mean, basically, many of you might have been educated by Professor Brian Steele. I know Professor Brian Steele was an absolute giant in our field in the materials department at Imperial. And Professor Steele basically thought, why can't I change from what is a very conventional ceramic technology to something that's more robust and also can be lower cost? And that started this whole journey. And it all started with a small coupon whereby they were able to put it on a metal and sinter it and be able to get a dense electrolyte at the lower temperature that was needed. Obviously, since then, we've come a long way. We've matured the technology, but that's what started it all. Professor Steele obviously is no longer with us. He passed away. But about a year back, we celebrate celebrated the 20th anniversary of this. And the other founders, Professor John Kilner, Professor Nigel Brandon, Nigel's still the Dean of Engineering at Imperial, and Professor Alan Atkinson, they all came and they gave us a fantastic view of how it used to be, and seeing all of the 500 people in that arena, it was a very emotional moment, as you can imagine, and it was a very emotional moment for all of us too, hearing from them how something like this started and how we've taken it and brought it all the way. So yeah, so we have very strong relationship with Imperial. Our founders are from there, and we obviously talk to them quite a bit even now as we go through our technology development and our successes. So, continuing with that, we now have a chair at Imperial and the Royal Academy of Engineering, where Professor Stephen Skinner, also in the materials department, is standing in the middle in this picture here. We work very closely with Imperial on lots of different topics, and I'm also a visiting professor at Imperial, and obviously we do a lot of great things with Imperial. So our Imperial relationship continues to grow, and it's fantastic for us and for Imperial. Now, the key about our technology is that, I mean, if you look at the world of fuel cells and electrolyzer, there's the alkaline and PEM proton exchange membrane fuel cell, which runs at pretty low temperature. And so it is, and one of the advantages of running at low temperature is you can perhaps use it in, for example, vehicles like cars, but it's not very efficient. And it requires things like platinum for the electrodes because it's at such a low temperature. And so there's a cost barrier to kind of commercialization of that, let's say. And on the other hand is a high temperature solid oxide, which I talked about, which has yttria stabilized zirconia as the electrolyte. And that is very, very efficient. But one of the problems with that is because of the high temperature, it requires nickel-based alloys for the system. And so cost is again a problem. And also robustness is a problem because it's all ceramic and at high temperature. And we are in the middle in what we call the Goldilocks temperature. So just the right temperature. And so we can tick all of the boxes of not only low cost and robustness, but also high efficiency and fuel flexibility. And so that's a big, big advantage of our technology. And so I think this is from one of the pioneering papers from Professor Steele, which shows that gadolinium doped ceria is an electrolyte that even at lower temperature gives very high ionic conductivity. And that is the choice of material for our electrolyte that we've used. That's why our name Ceres Power, obviously based on Syria. And that basically causes the revolutionary performance of our technology, being able to perform at these low temperatures what we wanted to do for a fuel cell and an electrolyzer. And so, and the other thing that as I mentioned, is that we have developed the technology to be able to put it on a metal substrate. So we deposit these very thin layers on a metal substrate, and there are no precious metals in it, so the cost is low. But also one of the big benefits of this low temperature and the metal support is the robustness. So this actually behaves like a ceramic coating on a metal, and that means it has a very different property than others. So we can do lots of on-off cycles. It can take a lot of thermal stress, and all of these are advantages in making products out of this fundamental technology that we've developed that allows for our customers to really use this for many applications. So this shows a little bit the basic design. So we take about a 300 micron ferritic steel to which we do a lot of laser drilling. If you ever come and see our manufacturing facility, you will see how all of these things are made. And on top of that, we put our ceramic layers. So there are the electrodes, which are the Syria nickel cermet, then the gadolinium doped Syria. We do have an electron blocking layer, so we call it the composite electrolyte, and then a perovskite-based air electrode, All of these are mostly put down by high volume manufacturing processes like screen printing. So we've adopted that from the photovoltaic industry, and so cost is low. And obviously, over the 21 years, we've developed these formulations, and that's what we basically license to all of our partners so that they can make it. We call it like our Coca-Cola recipe because it's obviously very, very secret what we do, what we've developed, and this is what we license to our customers who can then take it and also the manufacturing process and then use it to make large plants to make this fuel cell and electrolyzer. And we are continuously improving this architecture, obviously. Because we're a licensed technology licensing company, our customers expect improvements, and we continuously improve this so that we have better performance, better life, lower cost, improved processing. And that's what our customers love about our technology. And the other big benefit of solid oxide fuel cells is its high efficiency. So inherently, there are no moving parts, and it is very typical just for an electrical efficiency to be about 65%. So that's quite a very nice proposition as a product for making power at a very, very high efficiency. And because of that high electrical efficiency, people want to use it for all of the things where you might imagine where you need high efficient electric power at low cost. Also, the other big advantage for using this is you can use the heat. So if you combine the heat, the total efficiency of a combined heat and power system could be about 90%. And that's again a very big advantage for using this technology. So the other advantage of using solid oxide electrolyzer is also the efficiency over standard technologies like PEM and alkaline. And so if you can, even from water, we have high efficiency thermodynamically, but if you use steam, we can get even higher efficiency. And if you can couple it with processes like when you make green steel or ammonia plants where you can integrate the heating, you get about 25% more efficiency from a solid oxide electrolyzer. So both as a fuel cell and as an electrolyzer, we have a huge advantage of efficiency that makes this technology very, very attractive for our customers. And of course, we continuously are improving the technology. As I said, today we're working on V7, and in R&D, we're doing the development that's required, that our customers require, and we've improved the fundamental of the performances and the life over the years of this technology. And also, for if you take the repeating unit that I showed and put multiples of that, that basically constitutes what's called a stack. So it's like a battery. It's combined in series. And we've obviously made lots of improvements of it to lower cost, improve the footprint of each repeating unit, high current density, and basically more gravimetric and volumetric improved power density. So all of those improvements allow for lower cost for our customers, and that's what we are giving to our customers. And the other thing I talked about is the fuel flexibility. So that's one of the big advantages of using this technology is that you can use it with the fuels you have today, which are low carbon. So things like natural gas, but you can combine it with also hydrogen, but also in the future, you can use it with totally clean hydrogen or new fuels like biogas, e-methanol. Ammonia is another fuel which people are talking about a lot as a hydrogen carrier. Then also a liquid organic hydrogen carrier is something that people are talking about for shipping. So all of those can be fuels that we can use. So people call it a no regrets technology. So you can use it with something that's available now. And as you go to the future, you can change into new fuels. And one of the advantages of this technology is you can take some amount of impurities that are in the fuel, and we are quite robust to it. In fact, things like carbon monoxide, we can use it as a fuel. So that's another big advantage of using this technology. And so the vision is using the same electrochemical stack and system. You can use it for fuel cells, which are shown in the left. And the big applications there are AI and data centers. So with the kind of the onset of AI and, and the need for data centers, the demand for electricity is really going to grow exponentially in the next few years. And solid oxide fuel cells are absolutely going to be a part of meeting that demand all around the world. Also for distributed power and also for shipping. Shipping is a huge application where there are mandated needs for regulations for making lower emissions, and people are looking at all kinds of fuels from LNG to ammonia, and this is a real attractive application for us. And we have partners in this field who have already licensed our technology. So Doosan, they're in South Korea. They're one of the fastest growing fuel cell companies, and they have taken our technology and they are manufacturing in South Korea. Then Delta are a quite very big company in Taiwan, and they have also licensed our technology for both fuel cells and for electrolyzers, and they are putting in plants in Taiwan. And Weichai, who are a Chinese company, who are the world's largest or China's largest manufacturer of diesel engines, who are also taken our technology and licensed our technology. So similarly, just like we've done it for solid oxide fuel cell, the same kind of business model and the same kind of IP licensing uh, we are doing for green hydrogen, where you will use the renewable energy in, and you're going to use it for the hard to abate sectors like green steel, where you absolutely need it to reduce what today uses carbon, for green ammonia, where the Haber-Bosch process needs a lot of hydrogen. And if we need to meet our net zero targets, we have to use green hydrogen and synthetic fuels, which are absolutely needed for example, if you want to decarbonize the aviation industry, where you need sustainable aviation fuel, what's called SAF. So for all of these things, the green hydrogen that is made from our technology are needed. And one of the nice things about all of these sectors is you can have some integration with for example, the ammonia plant or green steel, where you can use the heat. So the efficiency benefit can also be used very much to use this. So if you look at a little bit the need for electricity, which will grow over the next years till 2050, you clearly see it as a growing industry. And for all of the things I just said, data centers, LNG for power and shipping, commercial buildings, industrial electricity, and there's a huge demand for it all around the world. And we have partners in it who have already licensed it, and it's growing. There's a lot of interest in this from other partners also. And similarly, in the green hydrogen that I talked about and the sectors I talked about, I mean, even if you look at steel, ammonia, and sustainable aviation fuel, almost 50% of green hydrogen would be required for that in these hard to abate sectors and other industries which absolutely need it for decarbonization. So it's a huge market, and it's about 3,769 gigawatts are expected in 2050. And if you look at it, it's a global play, really, because a lot of these are going to happen in many different countries where, for example, renewable electricity is very cheap, and they want to kind of grow their infrastructure based on that to make things like green ammonia and ship it everywhere in the world. So with our licensing model, we are very well suited to kind of look at it globally for manufacturing, but to be used anywhere in the world. And so for that, we have been developing not only the repeating unit, not only the materials technology, but also the stacks, then putting it together as a design for a stack array, then a module which will be a megawatt, and then hundreds of megawatt to gigawatt for plants. And in each of these areas, especially the large modules and plants, we are working with EPCs so that it can be taken all the way from what we do kind of in the lab to the design to kind of implementing it in actual chemical plants, which will make up for the gigawatt type of sectors. And one of the advantages we have is because we've been doing this for our fuel cell is the robustness, the number of hours we have used, and all of those learning, the robustness of emergency stops, load cycling, which is very, very important because if you are connecting it to, let's say, solar and wind, you would need to make those load cycling transients to be able to produce what you need to produce for green hydrogen. And similarly for data centers, as you need the demand for suddenly accelerating your ramp rate, we can do that with this technology. And the other big advantage is having worked through all of this, we know that there are no special handling requirements. So there's an example of customer fleet data, and we get a lot of these, and we use this to understand our technology and our products better and make improvements. And as you can imagine, the life of these things would be 5 years, 7 years, 10 years. You cannot run these things for that long to make improvements. So we use a lot of knowledge that we gain from things we get back from our customers. We understand the mechanisms of it. We model it. We make the improvements so we can make better products for our customers faster and obviously and in need for what is required for their needs for the future generations. So this shows a little bit some of the different products that are coming out from this technology. And we have over 2 million accumulated hours over multiple applications. The one in the center here is a megawatt scale solid electrolyzer from our technology. We are working with Shell. This is actually in the Shell R&D site in Bangalore, India, where they are running it. So this is in a container. So that was one of the first ways of doing it. Also, you see here the Doosan solid oxide fuel cell stationary application. So this is about 300 kilowatt, and two of these make 600 kilowatt that Doosan is running, and then this will be targeted towards the, for example, the data center market. There's the Doosan SFC Marine unit, which again, they're doing it for marine applications, which, as I said, are very, very important for fuel cells. So we are looking at multiple applications with multiple partners, all working towards, with our technology, going towards that. And of course, we are looking at improving life. So this shows in electrolysis, we're running our units. And as you run them, we run them in what's called the thermoneutral voltage. That's the maximum efficiency point at a high utilization, at a very high Faraday efficiency. And we are getting what we expect out of life, where if you run them, you'll get 50 to 60,000 hour life, which is kind of what our customers want out of our technology. And the other big point that everybody wants is robustness. And that's a unique feature in our technology that if you suddenly do an emergency stop, we are very robust to the immediate kind of cooling down and then heating it back up after that. And this is an advantage we have over other solid oxide fuel cell, which makes this technology very, very attractive for our customers. So here you see 60 emergency stops with almost no loss in performance, which is really, really attractive to our customers. And also, like I said, that is also very important for doing transients. And one of the things that is very attractive about our technology for hydrogen applications is we can meet real world renewable profiles efficiently. So as you can imagine, if you're doing it where you're combining it with solar and wind and you want to make ammonia using the green hydrogen, you would need to have I have this transient, so to be able to make green hydrogen in the most efficient way. And we've done a lot of modeling based on the operations we do. And as you can see, we have very good efficiency of making 47.8 kilowatt hour per kilogram across these kind of load cycles. And then that's without integrating it with any heat or any source of heat. So that is again something, and that is very, very good because when you compare it to what's out there, which is alkaline electrolyzers, this is competitive or better than that. So over the last year, we've been building the building blocks for what is required for a green hydrogen plant. So that starts from a 30 kilowatt stack, then to a stack array module, which is 24 stacks pressurized, and then what we call an electrolyzer module, which is 12 of those stack array modules together, 288 stacks, 8.64 megawatt. So we are working with Atkins Realis, who are a EPC, to kind of make this so that it can be implemented in actual plants for making hydrogen in a chemical plant. So this shows the 100 megawatt plant blueprint, making very highly efficient, less than 40 kilowatt hour per kilogram, and all of and that's kind of a rendition of how it's going to look to make that. And the plant is going to give hydrogen at 30 bar pressure, which is a requirement for making this. So it's got all of the compressors, all of the balance of plant providing hydrogen as it would be green hydrogen using our technology. And obviously, we've done the levelized cost of hydrogen for it, and it is quite attractive. We have found how this can be made into a very attractive proposition using not only the first time, but also the nth version of it, comparing it to other competitive technologies that are there for hydrogen production. And then we've also looked at a bigger plan, because if you want to make ammonia, people have said, well, that's quite small. We need 400 megawatt plants and 265 tons per day. And so we've looked at it, and actually, four of those, like I said, are going to be combined. That's big enough, like a 6 football pitch. And when you look at all of that with all the compressors, all of the balance of plant, we actually get benefit by doing it at scale like that, because now the energy modules are actually a bigger chunk of the cost. And so because we are quite cost effective there, the vertical scaling really helps. And and if we look at it using cheap electricity, where let's say we're going to make it somewhere where solar is really cheap, we can really meet the competitive costs that have been stated by the futuristic, let's say, the Department of Energies and the different European Union institutions, what is possible over time to be able to do these things. And so that shows you a vision of how we can do it. Now, where are we going to make it? And there also, we're making great progress. So in, for example, Doosan, who licensed our technology, have now built a 50 megawatt factory in Korea. You see the site. I mean, 2 years back, there was nothing there. It was basically a marshland. In just 2 years, they have put it into a completely fully automated factory. I was there last October. It's fantastic to see. You press a button and basically fuel cells come on the other side, fully automated, based on our technology and all of the work we've done. And they're taking it and they are ramping it up, and they want to ramp it up even further. Similarly, like I said, our other partners in Japan and in Taiwan are also doing the same thing. So we have partners all around the world. We're also working on green hydrogen with companies who are experts in this, like Shell. And we've also, I think I mentioned earlier, the SAM, we have licensed it to a company in India called Thermax. So we have multiple partners all around the world. And this slide kind of shows that we're working with partners to scale it at pace globally. So Doosan, I just talked about. Denso, they're part of the Toyota group. They have licensed it for solid oxide electrolysis in Japan. I'm actually going to be in Japan next week. So we are working with all of our Asian partners. In Taiwan, I talked about, we have Delta. In China, we have Weichai. And in India, we have Thermax, who have licensed the SAM to look at it. So this is the way we're accelerating market entry of this product with multiple partners all around the world. And we are looking for more partners everywhere, including the UK, Europe, America, everywhere. So just to summarize, we have a world-class UK technology spun off from Imperial College, which we're all very, very proud of. We are working with multinational manufacturing partners. We have a global footprint across multiple countries with multiple factories being built. We are 500 highly skilled team members here in the UK, many of them in Horsham, West Sussex, and some of them in Redhill. And we're proud to be a high growth company with multiple products in the pipeline for solving climate change. So with that, I'll be happy to take any questions and or any thoughts you might have. Thank you very much for your time.
Well, thank you very much, Dr. Mukerjee. Can I encourage people at this point, if I forgot to do it at the beginning, if you do have a question, you might like to type it in to the chat box, because that makes it easier and quicker for us to go through the questions rather than have people put their hands up. In the meantime, can I ask a preliminary question, if I may, while people get their other questions typed in? How do you start up a cold fuel cell in the morning? I mean, you need to get it up to 600 degrees or thereabouts to get the hydrogen burning. How does that go?
So very good question. So the way we do it is we basically take a little bit of the initial hydrogen or the initial fuel. We pre-combust it, let's say, and we use heat exchangers with air that the air then flows on into the fuel cell. And then that's how we heat up the fuel cell. And it can be done quite fast, depending on how you want to do it. So basically, thermally, we heat it up using air, warm up the air, basically. Yeah.
Hot air, right? Good.
Hot air.
Okay, got that. Let's see if there are any other questions yet in line.
Nothing yet, Alan. Could I ask a question?
Go ahead, Bill. Sure.
So I'm really interested to hear the operating time of 50 to 60,000 hours that you mentioned. Is there any maintenance activity on the kind of the fuel cell its own right? Obviously, there's maintenance on the whole plant, but that would be interesting to know.
Yeah, I think that's a very good question. So there are some things that needs to be changed. So, for example, not in the fuel cell per se, but we use a desulfurizer to take out any sulfur from the natural gas, for example, if it's going on the fuel side. So that is changed every couple of years, depending on kind of how large the desulfurizer is. So that is a standard maintenance that's done that can be done. We have filters on the air side, so to take away particulates. Let's say depending on where in the world is being operated. So let's say if it's in Korea, one of the things we learned the hard way is you need to change your particulate filter every now and then, especially if you're close to an area where you have some of those things. So, but those are quite standard kind of balance of plant. You don't have to do anything to the fuel cell. You can take it out and replace it. Yeah.
Okay, thank you. There's a couple of questions, Alan.
Oh, are they? Where are they? 3 new messages. Are these they? Okay.
In the chat.
Okay. Howard Bromley. Good. I'm glad Howard's here. Howard, pros and cons of SOFC versus batteries was his question, I guess.
Yeah, I think depends on which field you're talking about. I mean, so in the automotive field, let's say there was a lot of talk about batteries versus fuel cells and mostly low temperature fuel cells. And I think my opinion is, batteries have done really well, and I think that's great because I think we need to decarbonize it with batteries. But in the sector we are looking at, in the stationary applications, and also in making green hydrogen, like I said, to hard to abate sectors, you cannot do it with batteries. You absolutely need something that's that's can be used for these kind of scale and these kind of with these kind of fuels. And clearly their fuel cells, like ours, has a very high efficiency, and so will obviously be I think the area where there perhaps is a little bit more debate are things like, for example, long haul trucks. And so there's batteries that people do talk about. And I think one of the disadvantage of batteries in long haul trucks is just the weight of the batteries or the cost. So people are certainly looking at fuel cells for that. Often you also see you can combine the two. So fuel cells can be used to charge the batteries. So we did a thing with buses where we actually used it as a range extender to charge the battery, which was very, very attractive for doing that, something like that. So you didn't have to heat it up immediately, but you could use the high efficiency electricity to kind of charge the battery. So I think that's where it is. But I would say for things that are replacing, let's say, diesel engines of some kind of hundreds of kilowatts going to for shipping, clearly, I think the kind of fuel cell that I just showed you has a much more attractive proposition than batteries. But for things like automotive, batteries certainly are the ones of choice.
Okay. Now then, we have another question from Carol, who says, do you envisage any domestic use for this technology?
Yes, I think that's a very good question. So in the early days when we first started, we actually were doing a 700-watt micro CHP, which basically means if you put it in your home, it replaces your boiler, it takes care of all of your electricity needs and all of your heating needs. Japan did a lot of that also, and so some of that was there. But I think the challenge for doing it at home is the price has to come much, much lower without government subsidies. And so eventually someday I can see that happening, absolutely, with also things, fuels like hydrogen and things like that. But the applications I just showed, I think, are the first applications for something like this, and then eventually it can come. But of course, even heat pumps are very, very attractive. So I think
Yeah.
many of these solutions will play together. So
Okay, thank you. And Howard has come back with another question about
thank you.
what sort of plant would run SOFC in both directions. Would it be more likely to be hydrogen for electricity?
Yes, so I think that's again a very good question, and a lot of people are looking at this reversible operation of SOFC and SOEC. And I think the first thing to say is the people who would like to run this, and it's not a very it's more of a niche applications, are people who are remotely there and would require, let's say, ammonia or something else, or would require hydrogen. And I think they would like to be off grid, right? So if you want to be off grid and you want to run it in reversible mode, there are some advantages of doing that. So that's kind of where a lot of people are focused on, especially if you have an application where it's difficult to connect to the grid, and then you kind of need something like this. You can also imagine people who would like to have storage, so you could run it in reverse, store the hydrogen, and then use the hydrogen to run it. So that's another way of running it. The thing that complicates it, if you want to do both, your balance of plant obviously gets a little more complicated, and it adds cost. So if you're just needing hydrogen or you're just needing electricity, you won't do that. You will do that if you needed both, because it's slightly more complex and it adds a little more cost to be able to do a reversible one. So, but in the areas I just said, you could use it, yes.
Do we have any more questions from anyone? Please keep typing them in. Can I ask another
Sure.
until the next question appears? In one of your slides, you showed, I think, the efficiency as a function of the temperature, the running temperature of the fuel cell. Can I ask, how do you control the temperature of the fuel cell in each direction?
Yeah. So I think that's again a very good question. So the way we do it by controlling the air, basically. So the inlet of the air temperature, if we control it. So the fuel cell by itself, when running in a fuel cell, the process is an exothermic process. So it gives out heat when it's making power. So you control the inlet temperature, it gives out heat, as you can imagine. So you can also have a feedback loop on the external temperature, to the outlet temperature, let's say. So you have an understanding of the temperature window in which it's operating. What makes it very interesting is that if you use natural gas, then the process of converting methane to hydrogen is an endothermic process, which means it requires heat. So what we have done very cleverly is we've combined those two within the fuel cell to be able to get the maximum efficiency possible. And we control the temperature by the feedback loop and then controlling the inlet temperatures and the outlet temperatures.
Right, right. I see. Okay. Right. Now back to our audience questions.
Yeah.
We have a general question from Mr. Hurley. Where do you see hydrogen in the clean energy mix? The public is aware of the failure perhaps of offshore wind auction and a cooling of energy behind renewables from a commercial point of view, despite the economics being reported as favourable. I notice your share price has declined over the past 4 years. Oh dear.
So I think what I'll say is I think if we want to reach our net zero goals, energy is required. And I think, and not just net zero goals. I mean, if you look at now the demand for energy with AI, I think clearly there is need to be growth in energy. So both electrons and for decarbonizing the hard to abate sector, just like I said, also we require green hydrogen. So I think both of those are absolutely essential. And I think, I think we all have a role to play there for to introduce these products. And once they become part of the mix, like all new technologies, it will be adopted more. I think people will understand the need for these things. And obviously the geopolitics, the politics, all of these things will play a role, and we all have to play within that. And but the essential thing that I think we all need to understand is that more energy is required, and clean technologies and clean energy will be required to decarbonize some of the things which are legal. We have signed up for net zero, and that's absolutely essential.
Okay, thank you. Another question is from Henry Weatherburn asking, do you have any plans to recycle heat generated by AI centers?
Yeah, I think it's a very good question. I mean, I think wherever we can use heat, we would like to. So I think data centers do produce heat. So I think that's something. So depending on what you're using it for, uh, people have also talked about using fuel cells to kind of using it as a little bit of air conditioning for the heat generated. So there are multiple applications. So after the first use of just using it for making electrons or giving hydrogen as a fuel, you also want to then integrate these systems as much as possible and get the best benefit. And that's certainly an area that is going to be looked at.
Okay. I think we're running out of questions from the audience so far. Keep thinking, audience, please. Another comment or question that came to my mind as you explained your exploitation strategy, which seems to be succeeding very well, but in particular in the Far East. And it would be nice to see some entrepreneurial action from people in the UK, as well as people in Europe and the US. You did mention those in passing, but how is that going? Does that look optimistic, or are there generic reasons why that's slower to happen?
I think we would love customers everywhere. So I mean, I think maybe it's a call to the friends of Imperial to kind of show your entrepreneurial spirits maybe. But jokes aside, absolutely, I think we would love to see this factories being built everywhere in the world. And as you could see in that map, I think yes, we would like it in Europe and in America, even in UK. And so I think what we do see is in Far East and in Asia, they are, well, let's say that in manufacturing at least, they seem to be willing to go faster and and in some ways, and we are happy and excited about that. And obviously that's great, but we have people talking to everywhere in the world, and whoever would adopt this technology, we would be happy to give it. And yeah, absolutely.
Okay, can I ask a kind of follow-on question to
Yeah.
that around the inherent technology? Are there any spin-off areas? Because obviously you've got a focus, but is there anything you've learned in the in the kind of development of the technologies and the manufacturing where there are some spin-offs?
Yeah, I mean, obviously, we are very, very focused on kind of getting it, out there, as you can imagine. But you can also imagine working through all of these things, challenges that we have worked on. We have a lot of core knowledge about doing these things, and I would say the core knowledge that is very, very important that we've developed is how can you put ceramics on metals to create something that really works well
Mm,
electrochemically, right?
mm,
And I won't go into what those kind of spin-offs could be, but you can imagine that there are a lot of things where you could use more robustness, use those kind of things. So we often get requests or things from universities and other people. So could we look into those kind of things? I just think because we are so laser focused, because we have to make this work. So we haven't gone into that, but certainly that's a very good question and something from time to time we think, we could do it. Yeah, absolutely. So.
Yeah, I kind of mention it because, like organizations like McLaren Racing, whilst
mm.
their focus was on racing cars, they've become a
Yeah,
high-tech manufacturing facility,
yeah, that's a very good
possibly
point.
where they
Yeah,
make more
yeah,
of their money these days.
money. Yeah, that's true. Yeah,
Mhm.
exactly. Very good point.
Okay,
Well,
thanks, Bill. We have another question from Howard, who's asking what sort of volume of hydrogen store would be required to run a typical fuel cell for, say, a week or a month, versus the volume of the fuel cell plant itself, e.g., for a 1 megawatt plant, for example.
Uh, I have to do the numbers, but I mean, I think, uh, let me see if I open my presentation. I think we talk a little bit about. So if you look at this plan, this producing 265 tons per day of ammonia, and this is a 400 megawatt plant, right? So I think you can basically get an idea of if it is, let's say, about 90% efficient, of a 400 megawatt, you can do the
Mm.
calculation of how much steam you would require to produce the hydrogen you require for a 265 tons per day ammonia. Hopefully that's helpful.
So how much of the steam gets converted to hydrogen?
The steam gets converted to hydrogen, let's say at a utilization of roughly 75%.
Oh, really? Okay.
Yeah.
Mhm. Yeah. Yeah.
So
Okay.
roughly you can
Good.
do the math and you can calculate from there.
Yeah. Thank you. So in your business model, you've clearly been very successful so far in licensing your technology to a range of different customers, as you mentioned.
Yeah.
Does that usually also involve ongoing consultancy and support from you to the customers, or do they take it and then run with it themselves in general?
No, I think a very, very big part of it, Ellen, is the ongoing relationship that we continue to work with them to take them in their journey because
Okay.
it's such a kind of a new technology. I mean, many of these companies have, let's say, ceramics expertise, mechanical engineering expertise, electrical expertise, and manufacturing expertise,
Yeah.
but still they require our expertise to work together with them for not only transferring the technology, but also as they implement it and then they make it into whatever they make it, products, plants,
Yes. Yes.
manufacturing plants.
Yes.
So
Yes.
certainly that's a very big part of this. And they know they're talking to world experts and they really love that too. So I think
Mm.
we often say that our customers come to us for technology, but they stay with us for the people. And I think that's
Mm.
true.
Mm.
That's a very big part of doing this kind of a business. Yeah, it creates bonds which are very, very strong, and they need us, and we need them. Yeah.
Yeah, yeah. Good. Well, that's presumably a source of ongoing revenue, I would imagine,
Yeah,
for
and so
Ceres.
yeah, exactly. And I think yeah, and we depending on what they need, we create some kind of a contract to help them in their
Yes,
journey. Yes.
yes, yes. Okay, right. I think we've run out of questions. Howard has an add-on which said he meant to create, I mean to create electricity. Howard, you might want to unmute yourself and ask your question if I didn't catch the correct meaning.
Okay, so maybe I understand what Howard is saying. So I think the way to think about it, Howard, is that if you put natural gas in, the efficiency of a solid oxide fuel cell is about 65%. So you look at the thermal energy of the natural gas, and 65% of that will be converted into electricity. That's the efficiency. So you can calculate that. The rest of it is heat. So you can use that also in some industrial process. But the simple calculation is you just take the heating value of, let's say, natural gas, and 65% will be converted into electrons. So that way we calculate the amount of natural gas.
I guess
Did I
I was
answer
thinking.
the?
I guess I was thinking of something like a data center with one of your fuel cells. I mean, how much hydrogen would they have to store, or how many railway wagons of hydrogen would have to turn up per day?
Yeah, so they won't store it. It will be piped in. I mean, for example, a lot of these things would have piped in natural gas as a starting, or LNG, or these kind of things. And one of the advantages of fuel cells over batteries is there's no storage. I mean, you can continuously feed it into your fuel.
Sorry, I'm assuming hydrogen because we want to decarbonize. But if you're using natural gas, what are you doing with the carbon?
Yeah, so there are different visions. So if you use natural gas, that's a low carbon proposition. Then you're gonna basically do carbon capture. So you can combine carbon capture technologies with that, and the CO2 that comes out, you kind of use it, you capture it. So that's kind of today, right? If you have natural gas today. If you were to use hydrogen, you could store hydrogen, but mostly what will happen is you would have to get to a point where you're actually bringing in hydrogen, or you're bringing in biofuels or something like that.
Yeah, and that's my question. How much?
Yeah. So I'm just saying that if you do the calculation, you will see what it is. I mean, it's not a humongous amount. It is something that you can do. But
I'm expecting that if a power station needs, let's say, a train load of coal per week, or a train load of heavy oil per week, or whatever, given the density of hydrogen, and I'm expecting it to require several train loads.
Yeah, and maybe that's true if that's the case, and I think that's why people are thinking more of using things which have higher energy density as a fuel cell. So, for example, Bloom Energy, we're one of our competitors in the US. They are putting these things for data centers using natural gas as a fuel, and so that's what's acceptable. I mean, so that's still quite a low carbon footprint. There's still a low carbon footprint because it's much better than what you have today. And you can combine it, like I said, with carbon capture, which in the US now they have the IRA, which gives you some cost benefits if you can do the carbon capture. So that is a proposition you can do. For using hydrogen, you need to have a way of making hydrogen cost effectively and supplying it. And you're right. And I think that world has not yet happened, right? So I think you can, however, think, like you were saying earlier, you can use an electrolyzer and use steam to make the hydrogen, and then you use that hydrogen, you store it. But I don't think you will bring in hydrogen in trains, do things like these. I don't see that happening.
Okay, well, I think it's becoming time where we need to allow you to go home or have a cup of tea or something.
Okay.
But I'm sure we'd all like to thank you very much, but in particular for your efforts and your talk. You've kindly agreed has been recorded, and we can put on the Imperial YouTube channel in due course. But thank you from me and everybody else who asked the questions. And I'd like to invite our Deputy Chair, Bill, to give a sort of formal vote of thanks.
Yeah, thanks, Alan. And Shubi, can you hear me? Yeah, thanks.
Yes.
Thanks, Alan. Thanks, Shubi, for a fascinating talk. Yeah, we haven't had anything on the topic of fuel cells, to my knowledge, in the history of Friends. So that's kind of encouraging. So I'm very pleased that we've had the topic. It's kind of personal interest of mine as well. So I think one of the things that kind of struck me when you mentioned it was going to the Doosan plant, and that comment you made about you press a button and out pop fuel cells at the other end, and it's interesting to see how that full integration of the manufacturing has been achieved there. So that says quite a lot for the adaptability, I think, of the technology. And it also kind of struck me, we've had a couple of visits to the School of Design Engineering at Imperial College, and Peter Charles talked to us a couple of times. I think one of the things he said, it's very easy to do a startup. It's actually really difficult to do a scale up. And to achieve the scale of like 500 engineers down in Horsham is a really significant achievement. So that's very much appreciated. So I think I'd like to kind of propose a vote of thanks. And what we try and do is, if people could unmute or put their hands up or do something, then we'd like to give you a round of applause in the usual way.
Mm.